Hello, and welcome to this lesson on one of the more advanced concepts in the quantitative section of the exam, and certainly one of the most concerning for many students I've worked with over the years, combinations and permutations. So we're going to begin by talking about the technical definitions for combinations and permutations first, before potentially uh, transitioning to a more almost like analog way of handling them as opposed to this technical direct formulaic method, because the technical method works when it works, but when it doesn't, it definitely doesn't. So let's first just define these terms. So a combination is a selection of a number of items from a collection of items in which the order does not matter. Now, a permutation is going to be a selection of a number of items from a collection in which order does matter. So oftentimes folks will just kind of remember a little bit of alliteration, knowing that P in permutation means placement, as in P matters. And that's like a simple alliterative mnemonic if you're interested. Now, why do we have a giant exclamation point here in the bottom right hand corner of the screen? Well, that's because that exclamation point means factorial, and factorials are important for the application of the technical combination and permutation formulas we're going to discuss momentarily. So what a factorial is it's just a product of n and all positive integers that are less than n. So for instance, for 5 factorial with the little exclamation point, that means the operations are 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, 20 times 6 is going to be 120, and then just times 1, and that's how you get 5 exclamation point. It's not a very excited number, it's factorial. So then we will turn over to what you may or may not recognize, which is choose notation. So what is choose notation? Well, first, we've got to understand what these little n's and r's mean. So the n means the number of items to choose from. So that is the number of values or number of items that are in the collection that we just mentioned. R is the number of selections to be made. So you might have folks say n choose R, or 5 choose 6, or 5 permutation 3, those sorts of things. So that's what where the nomenclature comes from. Now, the big C indicates that it's a combination. The big P means that it's a permutation where order does matter, because placement and P both start, or placement and permutation both start with P. So that's just if you see these sorts of terms in your GMAT prep, that's what they mean when you see this format of formula. Now, there are just formulas that will apply to those notations potentially. So if you're looking at a permutation with repetition, so that means place matters, and you can use the same value more than once. You just use the formula n, which is the number of options, raised to the r power, which is the number of selections. So let's consider an example. How many different combinations of 3 letters are there in the English alphabet? Well, we are selecting 3 letters from 26 letters in the collection. So n is going to be 26, r is going to be 3, and we just do 26 to the 3rd power, 26 times 26 times 26, which is 17,576. Now, that's not really all that realistic of a GMAT problem, because it's too easy, to be perfectly honest. You just know it's 26 to the 3rd because you just have 26 letters for the first, 26 letters for the second, 26 letters for the third. It's a very simple choose principle concept. Now, let's consider a permutation without repetition. So this time we have to have our n factorial divided by n minus r, that quantity factorial. So again, n is the number of options, r is the number of selections. So another example, how many different ways can gold, silver, and bronze medals be awarded to the top 3 of 6 go-kart racers? So we've got our 6 racers we could select from, the number of options are n, and we've got 3 selections for gold, silver, and bronze. But we have to think about this as placement matters, because if you try to give Jimmy the bronze when Jimmy came in first, Jimmy's going to be upset. So this is a permutation, not a combination. So then we just apply it into the formula. We've got 6 factorial over 6 minus 3 factorial. So that's going to be 6, 5, 4, 3, 2, 1, all multiplied together on the numerator with 3, 2, 1 in the denominator. The 3's, the 2's, the 1's will cancel. We're left with just 6 times 5 times 4. which 30 times 4 is 120 different ways. Now that we've seen a permutation without repetition, let's move on to a similar but slightly different situation, a combination without repetition. So here we're going to have n factorial, where n is again the number of options, divided by r factorial times the quantity n minus r, then factorial. So in this example, similar scenario, but slightly different. In this case, we're being asked how many different ways can three $25 gift cards be awarded to each of the top three of 6 go-kart racers. So this time, instead of getting gold, silver, and bronze, they're each just getting a $25 gift card. So that means order doesn't matter, because this time Jimmy doesn't care whether he comes first, second, or third, because no matter what, he just gets a gift card if he's in one of those 3 places. So we still have 6 racers, so n is 6. 3 selections of the identical $25 gift card for our R is equal to 3. Then we just plug it into the formula. So 6 factorial on top divided by 3 factorial times 6 minus 3 factorial. So we end up with 6 times 5 times 4 times 3 times 2 times 1 in the numerator, all over 3 times 2 times 1 times 3 times 2 times 1 in our denominator. Now, the way that you want to cancel this out, take out the 3, 2, 1 at the end completely, and then take out the 3 and the 2 here with the 6, because that's going to directly cancel out an entire numerator. And then you're just left with 5 times 4 is 20 ways. So a bit more complex here, but not overly onerous if you can memorize the formula for combinations without repetition. But then we get to combinations with repetition, and you can see this is quite a fun little formula. It is significantly more complex than the other ones, and you have to remember the exact equation, which is going to be r plus n minus 1, that quantity, factorial, divided by r factorial times n minus 1 factorial, where n is the number of options and r is the number of selections. So it can be hard to even just conceptualize what a combination with repetition is. So we have another example. And we start with just how many different ways can Brenda choose 2 scoops of ice cream from a selection of chocolate, vanilla, strawberry, and butter pecan. So we have to be careful, because chocolate and strawberry is the same as strawberry and chocolate, but chocolate and chocolate can still be chosen. I can just choose chocolate, chocolate, vanilla, vanilla, strawberry, strawberry, butter pecan, butter pecan. So it's just, there's a lot of different possible iterations that we have to account for. Now, if we remember the formula, it will work. So n is equal to the number of options, which is the 4 flavors, and R is going to be the 2 selections where repeat scoops are allowed. So then we just have to find the quantity up top first. So R plus N is going to be 6 minus 1 factorial. So that's going to be 5 factorial all over 2 factorial, because we're selecting 2 scoops, times the number of selections, which is going to be, times n minus 1, which is the quantity after the R. And so n minus 1, since we have 4 flavors, is 3. So we end up with 5 factorial on top. So 5 times 4 times 3 times 2 times 1 in our numerator. In our denominator, we have r factorial 2 times 1 times n minus 1, 4 minus 1, 3 factorial, 3 times 2 times 1. And those 3 times 2 times 1, just as they did before, are going to cancel out entirely. We then just cancel our 4 with our 2, and we're left with just a numerator of 5 times 2, and 5 times 2 is 10 ways. It's a lot going on. There's no question about it. And if there are fewer than 20 options in all of our answer choices, we may decide not to do this for one simple reason. It's not that hard to list them. So we've got a relatively complex scenario again. But you can alternatively consider writing out possible outcomes as initials in an orderly fashion to count them if you've got limited numbers in your answer choices, and you can see that you can probably just kind of list them out. So listing is not a horrible idea here, especially, again, if you've got answer choices that are fewer than 20. You might be able to just logically list them out in a more efficient manner than working through this rather convoluted formula. So you can see, we just list them out. CC, chocolate, chocolate. Vanilla, vanilla. Strawberry, strawberry. Butter pecan, butter pecan. So there's 4 options right there. Then you go through all of the options that have one chocolate. So chocolate vanilla, chocolate strawberry, and chocolate butter pecan. And then you go through the options that involve vanilla but not chocolate. So vanilla strawberry and vanilla butter pecan. And then you involve the ones that involve strawberry and butter pecan, but not the other two. So that's the last is strawberry butter pecan. And you don't have to count any with butter pecan because you got all the butter pecan outcomes already through counting out the other flavors. So again, two discrete different approaches with the combination with the repetition. And you can already kind of see how these problems can become a bit complex. So let's actually work through a sample combinations and permutations problem. So we've got the problem here on the left-hand side. As always, we set up the scratch pad listing the choices vertically A through E. We're going to skip to the end of the problem, figure out what we're being asked for, and in this case, we're being asked how many combinations of book report presenters would include Edward but not Fizbo. So just write that out. Shorthand, number of combos with E, not F, equals what? Then we read from the beginning, taking notes and setting up equations as we go, but we've got to be careful about the equations because they get complex pretty quickly. So we've got Declan, Edward, and Fizbo are in a class of 10 fourth graders if the teacher is choosing 4 of the fourth graders. So we know there's 10 total options. We've got must include Edward, but not Fizbo. So we've got 10 options, must choose Edward, cannot choose Fizbo, and we know we're going to choose 4. So you want to consider if the structure leads to an obvious and simple application of one of these choose notation formulas. And if it does, apply the formula. But be honest with yourself if it doesn't. And I would say that in this scenario, with just the amount of different restrictions required, we're going to want to choose the no option and instead visually represent the outcomes using spaces to indicate our selection. So let's keep on moving. So we're at step 4 here now. So we're going to draw a space for each selection to be made, and we're going to label any known restrictions. So what that might look like is E is for the Edward space, and then we've got 3 more spaces, as you can see here, for the not F or not Fizbo spaces. So then you need to enter the number of options that are available one at a time, starting at the most restrictive selection. And in this case, that's going to be the E, because there's only one Edward, and you have to just choose that one Edward. Now, then, when we take Edward out, because you can't have Edward being selected twice, and we don't have Fizbo, then it's going to be 8 students that are left after that for the first Fizbo spot, 7 students left after that for the second not Fizbo spot, and then 6 for the third not Fizbo spot. So we just have 1 as the number of selections of Edward, and there's just 1 available Edward, and then there's 8 left that are not Fizbo, then 7 left that are not Fizbo, and then 6 left that are not Fizbo. Then we have to ask, does order matter for the selection? And if the answer is yes, then it's simple. We just multiply across. But lamentably, the answer here is no. So we're going to have to divide by the number of equivalent outcomes at that moment of selection. So we're going to pick this up over here at step 7. So that means we only have 1 possible Edward. So we're going to have 1 divided by 1. But for the first not Fizbo spot, there are 3 opportunities to be selected if you're not Fizbo. You can go into one of the non-Edward spots. Then there are going to be 2 not Fizbo spots after the first not Fizbo spot is filled, and then only 1 not Fizbo left after the first 2 not Fizbos have been selected. So we end up with 1 over 1, 8 over 3, 7 over 2, and 6 over 1. So then we just have to reduce our fractions and multiply across. So we recognize that 3 and 2 in the denominators would cancel with the 6 in the numerator. So all we're left with is 8 times 7, which is 56. And that's how to do this in a more intuitive manner, rather than relying on taking a relatively complex structure and forcing it into one of those choose notation structures that we talked about. So again, if you know how to do it and it's simple, consider using those simple formulas from earlier in the lesson. However, if you can't define exactly how to fit it into one of those 4 formulas, line out your spaces and work through the problem in a more deliberate fashion, as we just did here with this one. So step 1 of the combinations and permutations process. Carefully read the problem to determine if a choose formula is applicable. If the answer is yes, apply the appropriate formula, solve it technically, it could go really quickly for you. Great, hooray. But if the answer is no, then you want to draw that blank for each selection to be made and label the known restrictions. Then step 2, and this is really only if you're going with the blanks, because after step 1 you're done if a choose notation formula is applicable. Then you want to place the number of available options at the moment of selection in each blank, and you always want to start with the most restrictive blank and consider different possible iterations if necessary as well. So, like if there was a way to say Edward is selected or some Declan is selected, then you might have to actually draw out one scenario where Edward's selected, one scenario where Declan's selected, and add the two together. So it can get rather complex, but you may have to consider different iterations. Then step 3, ask, does order matter? Because if order matters, then you're going to have to multiply straight across. If order does not matter, that's when you have to divide, and you'll divide the number in each blank by the number of available equivalent outcomes at that moment of selection, reduce your fractions, and then multiply across. So, good amount of discussion around combinations, permutations. Definitely have at least 2 distinct approaches that you'll want to consider. So let's move on over to the whiteboard and take a look at both a problem solving and data sufficiency example of how to apply some of these combinations and permutations concepts. So let's take a look at a sample combination and permutation problem solving question for the GMAT quantitative section. So you can see I'm still setting up our scratch pad the same way as always, and since they're simple numbers, I might as well write them out too. So we got all the way down to 60. We want to skip to the end, figure out what we're being asked to solve for so that we don't read the question twice. And we can see we're being asked how many different combinations of books could she return in order to check out something new. So just the word combination itself kind of indicates that we're dealing with combinations and permutation problems. So we're looking at just different book combos. And so then we just start taking notes. Francesca has checked out 5 novels and 5 biographies from her local library. So we know that N is equal to 5. My biographies is equal to 5 as well. If local library rules require that she return 3 of these books, so we are going to choose 3 books before she can check out anything new, and at least 2 of the books must be novels. So at least 2 books are going to be novels. And then we get to our question. So at this point, we said we always want to consider, could we just run with our choose notation formulas? And it's that at least here that indicates to us it's not a simple choose notation. And that's basically how you want to set it up. Because if it were a simple, let's say we know it's a combination, right? But if it was a simple, we've got to choose from 10 and then select 3. So 10, choose 3, something like that. That would indicate, yeah, let's use the formula. But it's not. We've got to do the novel restriction. We're going to have to think about the different possible iterations. So it's probably a savvy decision to say that's going to be overly complex and instead work through the spaces. So then, how do we do the spaces? First off, we know we're selecting 1, 2, 3 books, and we have to consider the different ways that we can select those books. So we know that at least 2 of the books have to be novels. So it's got to be novel, novel, novel. Or it's got to be novel, novel, and a biography. And this is that multiple iteration circumstance, because anytime you've got an or, you're going to have to add. So we're going to figure out the number of different ways we can do the novels and the number of different ways that we can do 2 novels and a biography. So the biography or the novel situation up here, this one actually does lend itself to a more direct 5 choose 3 circumstance. So if you want to use the formula here, that's fine. But just to illustrate how we do it with the spaces fully, we know that we've got 5 available novels divided by the 3 equivalent outcomes. We would then have 4 available novels divided by the 2 equivalent outcomes. And then we'd have 3 available novels divided by the only 1 remaining novel spot. So then we just cancel out the 3, this 2, and that 4 just becomes a 2, and 5 times 2 here is going to equal 10. Which again, if you want to use the choose notation here, that's fine. This one's simple. But then it's the distribution of the two things that makes it more complex, because the second iteration, we still have 5 novels, but now we only have 2 novel spots. In our second novel selection opportunity, we then have 4 novels remaining and only 1 novel spot. And then for our biographies this time, we've got our 5 available biographies and our 1 available biography spot. Same issue as before. We're going to take our 4 and our 2, cancel that down to a 2, work 5 times 2 times 5, and that's going to give us 10 times 5 is 50. And we have to add those two values to discover that indeed there are 60 possible ways to send back these 3 books to make sure that Francesca can check out a new book from the library. So you can see the spaces are honestly, in most cases, with complex GMAT combinations and permutations, a preferable methodology. Again, if you really like the choose notation, you saw it in the presentation moments ago, feel free to use it, but as soon as it gets overly complex, set up the spaces. It'll become second nature if you just practice this different approach a few times. So then, just scrolling down here, we've got a sample data sufficiency. So setting up this data sufficiency for Laurent. So we know that Laurent is cooking a meal for his dinner party if he will produce each of a single main course. So we're going to have a main, a side dish, and a dessert. And we're being asked, is the number of possible meals greater than 40? And this, of course, is a yes-no data sufficiency. So we just box that off so we don't lose sight of what we're looking for. And what we need, because we know how we're going to make our selections, we're going to have main, side, and dessert. So there is no overlap in selection. So there's no overlap in selection. So it's not that order matters, but you have to select uniquely a main, a side, and a dessert. You can't pick 2 mains, you can't pick 2 sides. So order matters just by virtue of there being only one of each type of selection. So what we need is basically to know is the number, is basically, if we just call them MS and D, so this is, MSD, is M times S times D greater than 40. So condition 1 says that Laurent will cook one of 7 main courses. So M is equal to 7. Well, by itself, that's not going to be enough, because I don't know if there's 7 sides, then yeah, we've got well over 40 dishes. But if there's only 1 side and 1 dessert, it's just 7 possible dishes. So that's going to be insufficient. Options are B, C, or E. Then condition 2 says that Laurent will cook one of 6 desserts. So that means my D is equal to 6. Again, for the same reasons M alone wasn't sufficient, neither will D alone be sufficient. So that's out. But when we combine the two, now we know that we're going to have to multiply 7 times 6. That's going to be equal to 42. And 42 is, of course, greater than 40. No matter what the number of sides is, we've already come to the solution that it is going to be greater, a greater number of possible meals, simply because the mains times the sides is 42. So this would be sufficient, and our answer is choice C. Go ahead and complete some practice on your own for these combinations and permutation style questions, both data sufficiency and problem solving, as you continue to improve your performance on another of the exam's more advanced concepts.